So in this lecture we are going to talk about neutrino oscillations. Now neutrino is something which we have come across before even in our nuclear physics class, and when we talked about something like beta plus and the beta minus decay and we wanted to know about the concept of the missing energy, we also considered neutrino at that time. When we talked about leptons and we talked about electrons, we saw that there is something which is coming into the picture which is called the electron neutrino, and similarly we have got the muon neutrino and the tau neutrino. So based on this we actually have studied a lot about neutrino, but neutrino oscillation and the mass of neutrino, all these things the research is still on, and initially when it was thought that neutrino was actually massless, very much well explained by the standard model, later on it was seen that neutrino does have some kind of mass which was detected by the experimental setup in Japan. So if we just look into the very basic thing, what we have here is the neutrino, and we usually divide them into three flavors. These are nothing but the electron neutrino, the muon neutrino and the tau neutrino, and at the same time there are three masses M1, M2 and M3. But we need to understand here that a single neutrino, let's say for example an electron neutrino, can actually have three different kinds of masses, which is basically referred to as something which we call as neutrino mixing. So this is a concept which also came up, and these things are actually not explained in the standard model. If we just recall the standard model, we know that it has got the flavors, okay, and we talked about more about leptons, and the latest particle added was boson, and then we also talked about the interacting particles for four different forces. But if we talk just about neutrino, why is it so hard to detect? In general, when we say there is a large amount of neutrino which is flying around all the time, and there are trillions of neutrino which is passing through our body every second. Now there are different sources of neutrino which we already know, be it the cosmic rays, be it the supernova explosion, be it the stellar formation and so on. But then these neutrino which actually continuously explodes our body is not really felt by us because their interaction with matter is very rare. So all the universe is composed of particles referred to quarks and leptons, and this is very much well explained by the standard model. So one of the drawback of the standard model is that they say that the neutrino is massless, but the fact is that in order to explain a lot of phenomenon, we need to say that neutrino must be having some kind of mass. So if you consider only quarks and leptons, and if we just say take an example of the hydrogen atom, we know that the hydrogen atom is composed of one proton composed of three quarks and one electron, which belongs to the lepton family, particle family. So you basically can have the leptons and the quarks coming together and forming an atom and so on. And neutrino are usually considered to be the neutral leptons. So they are chargeless, but they are a part of the leptonic family. The characteristics, however, or the properties of neutrinos was not measured for a very long time, for the obvious reason that it was so difficult to detect that the measurement instrument was not well developed. But with advancement of technology, more and more instruments came into picture, because of which even these low massless particle which was difficult to detect at the initial stages became possible to be detected. And then we came up with something which we call as the neutrino mixing. So in neutrino mixing, what happens is the electron neutrino is the mixing state of neutrino 1, neutrino 2 and neutrino 3. So basically we have got three kinds of neutrino which are mixed together. So when we say something as neutrino mixing, these kind of concepts are basically coming from quantum mechanics. Because when we talk about quantum mechanics, we are going into the subatomic scale, and the behavior is totally different from something which is more or less macroscopic in nature. So what happens is that in an initial reaction you might have a neutrino which is actually behaving, let's say, as an electron neutrino, and as soon as it hits the detector, the neutrino will give rise to some other kind of leptonic particle, and then the detection of neutrino is different, might be a muon neutrino or a tau neutrino. So it depends on the length of time for which it travels. So by the time it travels and reaches the final point, the neutrino actually will change, and this gives rise to a concept which we call as the neutrino oscillation. So in neutrino oscillation, what happens is you might have neutrino 1, neutrino 2 and neutrino 3. All of them has got a different frequency, let's say, because of the mass, because all of them might be having different masses. And at one point of time you might have an electron neutrino having one mass, at the next point you might be having a different mass altogether, which is actually the concept of neutrino mixing. But when we actually look into the property of neutrino, since they have some kind of mass, the wave property cannot be avoided. So neutrino exhibits the property of a particle as well as wave. So whatever concept we actually have for the electrons behaving as a particle and wave, and talking about the de Broglie wavelength and so on, these things are actually applicable even for neutrino oscillation. So if you consider the neutrino 1, the neutrino 2 and the neutrino 3, each will actually have different eigenstates that will travel through space as waves, as they have different frequency. So they have different frequency, they will travel through space, and then finally if there is a mixing, the final output wave that we actually get is nothing but which will look something like this. So these are nothing but interference pattern or superimposition of waves. So how do we determine the flavor of the neutrino? So the flavor of the neutrino is determined by the superposition of the mass eigenstates. So we can actually have all the eigenstates and we can actually consider the superposition of them, and then we can actually determine the flavor of the neutrino. That is what is done experimentally. So what happens is the type of the flavor oscillates because the phase of the wave changes. So there will be an oscillation because of the phase change. And it means that if we are actually having one kind of neutrino and finally there is a change because of the phase, and we are finally detecting another kind of neutrino, that means the neutrino has changed from one type to another, and that is what is termed as nothing but the neutrino oscillation. So neutrino oscillation can occur or will occur as per theory when neutrino have mass and non-zero mixing. So there should not be any non-zero mixing, there will definitely be some kind of mixing involved when we are talking about these particles. So neutrino oscillation was discovered by the Super Kamiokande experimenter in Japan in the year 1998, and the atmospheric muon neutrino generated by the collision between cosmic rays and the atmosphere on the earth were observed. Okay, so the discovery of the neutrino oscillation verified that neutrino had a very small but finite mass. So finally they were able to discover neutrino or detect neutrino, and that actually proved the fact that actually neutrino had got a mass, but this is very small, but definitely there is some kind of mass. But then until that point it was thought that neutrino was massless. So after this discovery in 1998, which actually also fetched a Nobel Prize, the neutrino, the looking into the factor of neutrino was completely changed, and then neutrino oscillations were later observed using solar neutrino and the artificial neutrino beam. So if you are considering any kind of high energy experiment as conducted in CERN and all, they are also generating neutrinos. These neutrinos are also studied. The solar neutrino, which is a natural source of neutrino generation, was also studied, and finally this neutrino oscillation was observed. So if we just go back to the standard model, and if you look into this, we have seen to this table a number of times. If you look into this, what scientists are basically working on right now, or as per this topic, is something like here, right? So if you just go back, so what's important is the three different kind of neutrinos. But then if we just consider the neutrino, that's not enough. We also need to understand that there is something which is called the mixing of neutrino and the neutrino oscillations. So what happened is, like, the research started, and then people tried to detect the source of neutrino, and there are four different sources of neutrino as of now that we know. These are the solar sources, of course the atmospheric sources like the cosmic rays and so on, if you're using any kind of reactors and the reactor experiment that are being done, they also generates neutrino, and of course the accelerator neutrino. So if you're considering any kind of experiment, high energy physics, CERN experiment, proton-proton colliding and so on, these things will definitely have some kind of neutrino involved there. Now the standard model, what it stated that the neutrinos are more or less massless and chargeless and only undergo weak interaction. Well, the weak interaction fact is more or less okay, but then chargeless and massless, even the fact question of massless was actually questioned by this experiment, and later on it happened that as an evidence of mixing, neutrinos have been observed to change from one flavor to another during their propagation. So it basically starts from this end, and then midway you can detect it, and then you will be getting some kind of neutrino, let's say an electron neutrino, and then finally when this is the area where it is actually stopped or detected by another detector, we basically see that this actually gets converted into a tau neutrino. Please remember, this might not be a detector here, this might be the beginning of the reaction. Now you basically have an electron involved and you are expecting an electron neutrino, so that means this is something which you are expecting. But later on when you get the reaction, and if the detector is hit by the neutrino, there is generation of other kind of lepton, and finally the neutrino which can be predicted becomes a muon neutrino. So that means it has basically changed, or it has changed this flavor from one type to another, and this is called neutrino oscillation. So by oscillation means there is a change in the flavor of the neutrino that we have. So the concluding remark is that the charged lepton produced alongside a neutrino can be easily detected, right? So we can easily detect a charged lepton because this has definitely has got charge, more easy to detect than a neutrino. But we know that in order to go on with the conservation laws, there should be some other particle, and later on it was found out that this was nothing but neutrino. And then based on this charged lepton, the flavor was identified. So we can say that the flavor of the produced neutrino was, let's say, alpha. Okay, this might be electron neutrino, muon neutrino, tau neutrino, but let's say it's just alpha. Then what happens, similarly at the end of the path of length, let's say L, the neutrino reacts with the detector and then produces a charged lepton. Now then after the neutrino reacts with the reactor or the detector, sorry, it basically produces a lepton. Now we know that that lepton can again be detected. So once we determine the flavor of that charged lepton at the detector end, we finally say that the flavor of the neutrino has changed and it has become, let's say, beta. Now if this alpha is not equal to beta, okay, most of the time, see, these are all probabilistic, so it might happen that both of them will remain the same, but many a times it does happen that it doesn't remain the same. So if you are having a very large experimental setup in length, the same as has been set up in Japan and all, then by the time it reaches the other end, it has traveled a large amount of distance, and then this alpha and beta are not the same. So if alpha is not equal to beta, then basically the neutrino has changed its flavor in its journey, and this is what we term as the neutrino oscillation. So I know it's a bit difficult to digest, but as we know that quantum mechanics answers a lot of things, and everything is more or less based on probability. So you have to get the concept of probability and think about it. So in the next lecture I'm going to talk a bit more about neutrino. We are also going to refer roughly to the Nobel Prize that has been awarded in this field in the 21st century. Okay, that's all for today. Thank you.